Hello and welcome back to another video. Today I will continue my cloud architect learning path, and in particular I will continue my reliable Google infrastructure design and process course. I'm at 15% advances in this course. It's a long one as it has a lot of theory, many theoretical exercises, and it has no hands-on labs. It has only module quizzes. So it's a type of course which I'm not used to. Yeah, we'll go through it. There's a lot of information I have to memorize that can be useful not only for the exam, but also for the day-to-day operations as a cloud architect. Therefore, let's go. I will make a memorization effort here. In the last module, we had some ideas about how to structure the process where we define the features and the persons, the type of users which will use those features. Therefore, we try to create some example of personas and user stories, which then led us to define some KPIs, which can allow us to monitor our system and understand if we are actually achieving the business and technical requirements of the system. And that's it. We did all of this until now. And today I will focus on microservices design and architecture. Therefore, let's go. Let's have this introduction.
I'm Priyanka Varkaria, a developer advocate for Google Cloud. In this module, we introduce application architecture and microservice design. Specifically, you will learn about microservice architectures and how to decompose monolithic applications into microservices. The benefits of a microservice architecture for cloud-native applications is discussed and contrasted with a monolith. The challenges of decomposing applications into microservices with clear boundaries to support independently deployable units are investigated. You will learn how to architect for some of the major technical challenges of microservices architecture, such as state management, reliability, and scalability. Once a cloud-native microservice architecture has been chosen, the best practices for development and deployment are introduced based around the widely recognized 12-factor best practices. At the end of the module, we will go over a core component of the microservice architecture, which is the design of consistent, loosely coupled service interfaces.
Okay, let's go. Therefore, microservices.
Let's begin by looking at microservices in more detail. Microservices divide a large program into a number of smaller independent services, as shown on the right, unlike a monolithic application, which implements all its features in a single codebase with a database for all data, as shown on the left. Microservices are the current industry trend. However, it's important to ensure that there's a good reason to select this architecture. The primary reason is to enable teams to work independently and deliver through to production at their own cadence. This supports scaling the organization. Adding more teams increases speed. There is also the additional benefit of being able to scale the microservices independently based on their requirements. Architecturally, an application designed as a monolith or around microservices should be composed of modular components with clearly defined boundaries. With a monolith, all the components are packaged at deployment time and deployed together. With microservices, the individual components are deployable. Google Cloud provides several compute services that facilitate deploying microservices. These include App Engine, Cloud Run, GKE, and Cloud Run functions. Each offers different levels of granularity and control and will be discussed later in this course. To achieve independence on services, each service should have its own data store. This lets the best data store solution for that service be selected and also keeps the services independent. We do not want to introduce coupling between services through a data store. A properly designed microservice architecture can help us achieve the following goals: define strong contracts between the various microservices, allow for independent deployment cycles, including rollback, facilitate concurrent A/B release testing on subsystems, minimize test automation and quality assurance overhead, improve clarity of logging and monitoring, provide fine-grained cost accounting, and increase overall application scalability and reliability through scaling smaller units. However, the advantages must be balanced with the challenges this architectural style introduces. Some of these challenges include it can be difficult to define clear boundaries between services to support independent development and deployment. Increased complexity of infrastructure, with distributed services having more points of failure. The increased latency introduced by network services, and the need to build in resilience to handle possible failures and delays. Due to the networking involved, there's a need to provide security for service-to-service communication, which increases complexity of infrastructure. Strong requirement to manage and version service interfaces. With independently deployable services, the need to maintain backward compatibility increases. Now, decomposing applications into microservices is one of the biggest technical challenges of application design. Here, techniques like domain-driven design are extremely useful in identifying logical functional groupings. The first step is to decompose the application by feature or by function groupings to minimize dependencies. Consider, for example, an online retail application. Logical functional groupings could be product management, reviews, accounts, and orders. These groupings then form mini-applications which expose an API. Each of these mini-applications will be implemented by potentially multiple microservices internally. Internally, these microservices are then organized by architectural layer, and each should be independently deployable and scalable. Any analysis will also identify shared services, such as authentication, which are then isolated and deployed separately from the mini-applications. When you're designing microservices, services that do not maintain state but obtain their state from the environment or stateless services are easier to manage. That is, they're easier to scale, to administer, and to migrate to new versions because of their lack of state. However, it's generally not possible to avoid using stateful services at some point in a microservice-based application. It's therefore important to understand the implications of having stateful services on the architecture of the system. These can include introducing significant challenges in the ability to scale and upgrade the services. Being aware of how state will be managed is important in the very early stages of microservice application design. Let me introduce some suggestions and best practices on how this can be achieved. In memory, shared state has implications that impact and negate many of the benefits of a microservice architecture. The autoscaling potential of individual microservices is hindered because subsequent client requests have to be sent to the same server that the initial request was made to. In addition, this requires configuration of the load balancers to use sticky sessions, which in Google Cloud is referred to as sessionfinity. A recognized best practice for designing stateful services is to use back-end storage services that are shared by front-end stateless services. For example, for persistent state, the Google Cloud Managed Data Services, such as Firestore or Cloud SQL, may be suitable. Then, to improve the speed of data access, the data can be cached. Memory Store for Redis, which is a highly available Redis-based service, is ideal for this. This diagram displays a general solution that shows the separation of the front-end and back-end processing stages. A load balancer distributes the load between the back-end and front-end services. This allows the back-end to scale if it needs to keep up with the demand from the front-end. In addition, the stateful servers and services are also isolated. The stateful services can make use of persistent storage services and caching as previously discussed. This layout allows a large part of the application to make use of the scalability and fault tolerance of Google Cloud Services as stateless services. By isolation of the stateful servers and services, the challenges of scaling and upgrading are limited to a subset of the overall set of services.
Okay, so there's this crucial distinction between stateful and stateless services, which will determine if you need to keep in memory the state of the operation you're currently executing, or if the function that needs to be computed doesn't really need to refer to a system status when executing the operations. Of course, stateless are more agile, and the key here looks like to divide front end and back end in a way which allows the back end then to be subsequently divided in stateful and stateless services. Therefore, only the stateful services will need to have, for example, caching functions, the scaling logic for these two type of services will be different, of course, and they will also use different type of Google Cloud tools, or in general cloud tools. And therefore, it's interesting to start from this categorization first.
Let's discuss microservice best practices. The 12-factor app is a set of best practices for building web or software as a service applications. 12-factor design helps you decouple components of the application so that each component can be deployed to the cloud using continuous deployment and scale up or down seamlessly. The design principles also help maximize portability to different environments. Because the factors are independent of any programming language or software stack, 12-factor design can be applied to a wide variety of applications. Let's take a look at these best practices. The first factor is codebase. The codebase should be tracked in a version control such as Git. Cloud source repositories provide fully featured private repositories. The second factor is dependencies. There are two main considerations when it comes to dependencies for 12-factor apps: dependency declaration and dependency isolation. Dependencies should be declared explicitly and stored in version control. Dependency tracking is performed by language-specific tools such as Maven for Java and pip for Python. An app and its dependencies can be isolated by packing them into a container. Container registry can be used to store the images and provide fine-grained access control. The third factor is configuration. Every application has a configuration for different environments like test, production, and development. This configuration should be kept external to the code and is usually kept in environment variables for deployment flexibility. The fourth factor is backing services. Every backing service, such as database, cache, or message service, should be accessed via URLs and set by configuration. The backing services act as abstractions for the underlying resource. The aim is to be able to swap one backing service for a different implementation easily. The fifth factor is build, release, run. The software deployment process should be broken into three distinct stages: build, release, and run. Each stage should result in an artifact that is uniquely identifiable. Build will create a deployment package from the source code. Every deployment package should be linked to a specific release that's the result of combining a runtime environment configuration with a build. This allows for easy rollbacks and a visible audit trail of the history of every production deployment. The run stage then simply executes the application. The sixth factor is processes. Applications run as one or more stateless processes. If state is required, the technique discussed earlier in this module for state management should be used. For instance, each service should have its own data store and caches using, for example, memory store, to cache and share common data between services used. The seventh factor is port binding. Services should be exposed using a port number. The applications bundle the web server as part of the application and do not require a separate server like Apache. In Google Cloud, such apps can be deployed on platform services such as Compute Engine, GKE, App Engine, or Cloud Run. The eighth factor is concurrency. The application should be able to scale out by starting new processes and scale back in as needed to meet demand and load. The ninth factor is disposability. Applications should be written to be more reliable than the underlying infrastructure they run on. This means they should be able to handle temporary failures in the underlying infrastructure and gracefully shut down and restart quickly. Applications should also be able to scale up and down quickly, acquiring and releasing resources as needed. The 10th factor is dev production parity. The aim should be to have the same environments used in development and test staging as are used in production. Infrastructure as code and Docker containers make this easier. Environments can be rapidly and consistently provisioned and configured via environment variables. Google Cloud provides several tools that can be used to build workflows and keep the environments consistent. These tools include cloud source repositories, cloud storage, container registry, and Terraform. Terraform uses the underlying APIs of each Google Cloud service to deploy your resources. The 11th factor is logs. Logs provide an awareness of the health of your apps. It's important to decouple the collection, processing, and analysis of logs from the core logic of your apps. Logging should be to the standard output and aggregating into a single source. This is particularly useful when your apps require dynamic scaling and are running on public clouds, because it eliminates the overhead of managing the storage location of the logs and the aggregation from distributed and often ephemeral VMs or containers. Google Cloud offers a suite of tools that help with the collection, processing, and structured analysis of logs. The 12th factor is admin processes. These are usually one-off processes that should be decoupled from the application. These should be automated and repeatable, not manual processes. Depending on your deployment on Google Cloud, there are many options for this, including cron jobs in GKE, cloud tasks on App Engine, and Cloud Scheduler.
Nice. So, in few words, we have this framework called the 12 factors design, which helps to decouple components of an application, and this allows you to optimize the operations in developing, deploying, monitoring, and administrating a system. It reduces the cost, the job, the time, and the effort to keep everything ordered.
In this design activity, you're going to work on activity 4 of the design workbook. You will design microservices for your application. The primary aim is to diagram the microservices required by your case study application. Some of the things to consider are the microservice boundaries and state management, as well as common services. Use the principle we've discussed in this module so far. Here's an example diagram for microservices for the website and the mobile phone application of an online banking service. Draw a diagram similar to the one shown here for your case study.
Okay, mark as completed, and we put in pause the next video, and I have a link to my workbook, which is just a Google slide. Okay, and we need to go to activity 4. Okay, therefore we have to draw a diagram on the next slide showing our application's microservices and their connections. Okay, I will copy something from here, of course. And in our case, we will have a web user interface and a mobile user interface. We'll have, of course, an authentication service. Let's see if we can copy it here. Yeah. Yeah, let's get rid of this and this. Okay. Let's bring this one in front. Okay. Therefore, let's see. Just to have a brief recap, our application will be called Cicero, and it's a luxury local tour organized by locals. It's a platform which offers these luxury local tours. And one of the main entry point in this system is a link to a form. Therefore, we need a service. So it's a interview form service which will memorize in a customer database all the informations we need then to use to create some trips, which will then purpose in a subsequent stage. From the web UI, we have the trip director service. Let's say the itinerary creation, itinerary definition service. Okay. Therefore, then we will have itinerary definition service, interview form service. Then we have the itinerary view and modification service, which will allow our customers and our trip directors to continuously collaborate in the trip definition. Sorry, I changed page. Okay, and this itinerary definition here, we will need a database of the itineraries. Whoop. Yeah, and so this itinerary definition service will use itinerary database This will be also itinerary database. Here I will say that we have also access to the customer database. This is in view. Let's put shorter. Okay, view customer database. Here we'll make, we'll write the customer database. Oh, sorry. So this one becomes smaller. Okay, then what happens is that we'll obtain some informations which will be viewed and modified in the itinerary database. Then we'll have a reporting service and an analytics service, which will be accessed only by the administrators. Let's see if we have something else, maybe, which can be, yeah, like the photos. So the photos upload and the photos visualization service. Yeah, it's a cool one. So I would just photo service, multimedia sharing service. Yeah, maybe we'll, oh, what happened? I'm not sure. I will do like this. Okay, so here we'll get rid of this arrow and this one also. Wait. So we'll go with this and this. We'll bring them downwards here. Oh, fuck. Oh my god, I hate these softwares. They're really annoying. Let's see if now it can move. Yeah. So this will be multimedia service, which will be related to the itinerary service as it will access it. Therefore, we'll put an arrow like this one here. So let me put it shorter. Multimedia. I'm not sure. It will be maybe not a database, maybe a catalog. Bucket. Yeah, it will be a multimedia bucket. This one will be a data warehouse. And yeah, here the customers, the itineraries, and yeah, all the rest of this type of information will be stored in a database. Yeah, it's just a normal database. Okay. Therefore, this is another exercise. We can continue with these videos.
You were asked to diagram your case study application using microservice-style architecture. The number of microservices appropriate for application and recognizing the microservice boundaries is not obvious. Two programs might look similar, but their architecture might be considerably different based on the number of users, the size of data, security, and many other factors. Fewer services might make deployment and communication between services easier, but also make development and adding new features harder. Having more smaller services makes each individual service easier to understand and implement, but may make the overall architecture of your program more complicated. Like many things in life, you are looking for the right balance, trading off one type of complexity for a different type, hoping to make the system overall as simple and as maintainable as possible. Here is a sample diagram depicting the microservices of our online travel portal. I suppose we could lay this out in many different ways. There really isn't one and only right way to design an application. Notice, we have separate services for our web and mobile UIs. There's a shared authentication service, and we have microservices for search, orders, inventory, analytics, and reporting. Remember, each of these services will be deployed as a separate application. Where possible, we want the stateless services, but orders and inventory services will need databases, and the analytics service will provide a data warehouse. This might make a good starting point, and we could adjust as needed when we start implementing the application.
Okay, so nice point. This one, basically, we designed an application which has only two stateless microservices. All the other will write and make reference to some state in the system, which I don't know if we can avoid this. I think maybe yes, maybe not. We'll have a look later. For example, in the case of multimedia, I mean, we cannot avoid memorizing stuff, but at the same time, the service returning a multimedia object will only handle an ID of a multimedia related to an itinerary point. Therefore, yeah, I'm not sure if it's possible to avoid to use states, even if this is not a state actually. At the same time, it's just an object that has to be returned. So maybe in this case it can be deleted. We can avoid using anything. Okay. Whoops. Like the itinerary can't be avoided to be memorized in a database. Therefore, we need this. Okay. Let's go. Let's see.
About the design of microservices based on REST and HTTP to achieve loosely coupled independent services. One of the most important aspects of microservices-based applications is the ability to deploy microservices completely independent of one another. To achieve this independence, each microservice must provide a versioned, well-defined contract to its clients, which are other microservices or applications. Each service must not break these versioned contracts until it's known that no other microservice relies on a particular versioned contract. Remember that other microservices may need to roll back to a previous code version that requires a previous contract. So it's important to account for this fact in your deprecation and turndown policies. A culture around strong versioned contracts is probably the most challenging organizational aspect of a stable microservices-based application. At the lower level of detail, services communicate using HTTPS with text-based payloads, for example, JSON or XML, and use the HTTP verbs such as get and post to provide meaning for the actions requested. Clients should just need to know the minimal details to use the service, the URI, the request, and the response message formats. REST architecture supports loose coupling. REST stands for Representational State Transfer and is protocol independent. The HTTP is the most common protocol, but gRPC is also widely used. REST supports loose coupling but still requires strong engineering practices to maintain that loose coupling. A starting point is to have a strong contract. HTTP-based implementations can use a standard like OpenAPI, and gRPC provides protocol buffers. To help maintain loose coupling, it is vital to maintain backward compatibility of the contract and to design an API around a domain and not particular use cases or clients. If the latter is the case, each new use case or application will require another special purpose REST API regardless of the protocol. While request-response processing is the typical use case, streaming may also be required and can influence the choice of protocol. gRPC supports streaming, for example. Resources are identified by URIs or endpoints, and responses to requests return an immutable representation of the resource information. REST applications should provide consistent, uniform interfaces and can link to additional resources. Hypermedia as the engine of application state is a component of REST that allows the client to require little prior knowledge of a service because links to additional resources are provided as part of the responses. It is important that API design is part of the development process. Ideally, a set of API design rules is in place that helps the REST APIs provide a uniform interface. For example, each service reports error consistently. The structure of the URLs is consistent, and the use of paging is consistent. Also, consider caching for performance and resource optimization for immutable resources. In REST, a client and server exchange representations of a resource. A resource is an abstract notion of information. The representation of a resource is a copy of the resource information. For example, a resource could represent a dog. The representation of a resource is the actual data for a particular dog. For example, Neuer, who is the schnoodle, or Brie, who is the mutt. Two different representations of a resource. The URI provides access to a resource. Making a request for that resource returns a representation of that resource, usually in JSON format. The resource requested can be single items or a collection of items. For performance reasons, returning collection of items instead of individual items can be beneficial. These types of operations are often referred to as batch APIs. Representation of a resource between client and services are usually achieved using text-based standard formats. JSON is the norm for text-based formats, although XML can be used as well. For public-facing or external-facing APIs, JSON is the standard. For internal services, gRPC may be used, in particular if performance is key.
Okay. Let's continue with
Client
this.
accessing HTTP service forms an HTTP request. HTTP requests are built in three parts: the request line, header variables, and request body. The request line has the HTTP verb, get, post, put, etc., the requested URI, and the protocol version. The header variables contain key value pairs. Some of these are standard, such as user agent, which helps the receiver identify the requesting software agent. Metadata about the message format or preferred message formats is also included here for HTTPS-based REST services. You can add custom headers here. The request body contains data to be sent to the server and is only relevant for HTTP commands that send data, such as post and put. Here we see two examples of HTTP client text-based messages. The first example shows an HTTP GET request to the URL using HTTP version 1.1. There is one request header variable named host with the value pets.drenstorm.com. The second example shows an HTTP POST request to the URL /add using HTTP version 1.1. There are three request header variables: host, content type set to JSON, content length set to 35 bytes. There is the request body, which has the JSON document, name, Neuer, breed, schnoodle. This is the representation of the pet being added. As part of a request, the HTTP verb tells the server the action to be performed on a resource. HTTP as a protocol provides 9 verbs, but usually only the 4 listed here are used in REST. GET is used to retrieve resources. POST is used to request the creation of a new resource. The service then creates the resource and usually returns the unique ID generated for the new resource to the client. Put is used to create a new resource or make a change to an existing resource. Put request should be idempotent, which means that no matter how many times the request is made by the client to a service, the effects on the resource are always exactly the same. Finally, a delete request is used to remove a resource. HTTP services return responses in a standard format defined by HTTP. These HTTP responses are built in 3 parts: the response line, header variables, and response body. The response line has the HTTP version and a response code. The response codes are broken on boundaries around the hundreds. The 200 range means OK. For example, 200 is OK. 201 means a resource has been created. The 400 range means the client request is in error. For example, 403 means forbidden due to requester not having permission. 404 means requested resource not found. The 500 range means the server encountered an error and cannot process the request. For example, 500 is internal server error. 503 is not available, usually because the server is overloaded. The response header is a set of key value pairs, such as content type, which indicates to the receiver the type of the content the response body contains. The response body has the resource representation requested in the format specified in the content type header and can be JSON, XML, HTML, etc. The guidelines listed here focus on achieving consistency on the API. Singular nouns should be used for individual resources and plural nouns for collections or sets. For an example, consider the following URI /pet. Then a GET request for URI /pet/1 should fetch a pet with ID 1, whereas GET/pets should fetch all the pets. Do not use URIs such as get/getPets. The URI should refer to the resource, not the action on the resource. That is the role of the verb. Remember that URIs are case insensitive and that they include version information. It is a good practice to diagram services. This diagram shows that there is a service that provides access to the resource known as pets. The representation of the resource is the pet. When a request is made for the resource via the service, one or more representations of a pet are returned.
Nice. Okay. Let's continue.
Let's move on to API design. It is important to design consistent APIs for services. Google provides an API design guide with recommendations on items such as names, error handling documentation, versioning, and compatibility. This guide and the API stylebook are linked in the slides. For examples of best practices, it is useful to examine the Google Cloud APIs. Each Google Cloud service exposes a REST API. Functions are defined in the form of service.collection.verb. The service represents the service endpoint. For example, for the Compute Engine API, the service endpoint is https://compute.googleapis.com. Collections include instances, instance groups, and instance templates. The verbs then include list, get, and insert. To see all of your Compute Engine instances, make a GET request to the link shown on the slide. Parameters are passed either to the URL or on the request body in a JSON format. OpenAPI is an industry standard for exposing API.
Just a second, I want to examine. Okay, so service.collection.verb. So we have service compute. Nah, this is strange. So how does this work? I mean, I can see the verb in this case.
Request body in a JSON format. OpenAPI is an industry standard for exposing APIs to clients. Version 2.0 of the specification was known as Swagger. Swagger is now a set of open source tools built around OpenAPI that, with associated tooling, supports designing, building, consuming, and documenting APIs. OpenAPI supports an API-first approach. Designing the API through OpenAPI can provide a single source of truth from which source code for client libraries and server stubs can be generated automatically, as well as API user documentation. OpenAPI is supported by Cloud Endpoints and Apigee. The example documentation shows a sample of an OpenAPI specification of a pet store service. The URI is petstore.swagger.io/v1. Note the version in the URI here. The example then shows an endpoint /pets, which is accessed by using the HTTP verb get and will provide a list of all pets. Developed at Google, gRPC is a binary protocol that is extremely useful for internal microservice communication. It provides support for many programming languages, has strong support for loose coupling via contracts defined using protocol buffers, and is high performing because it's a binary protocol. It is based on HTTP 2 and supports both client and server streaming. The protocol is supported by many Google Cloud services, such as the Application Load Balancer and Cloud Endpoints for microservices, as well as on GKE by using an Envoy proxy. Google Cloud provides 3 tools for managing APIs: Cloud Endpoint, Apigee, and API Gateway.
Okay. Nice. So I've never worked with these tools. I've never designed and built APIs. I've never been in such operations. So it's cool to discover these. API Gateway, Cloud Endpoints, and Apigee.
Cloud Endpoints is an API management gateway which helps you develop, deploy, and manage APIs on any Google Cloud backend. It runs on Google Cloud and leverages a lot of Google's underlying infrastructure. Apigee is an API management platform built for enterprises with deployment options for on-cloud, on-premises, or hybrid. The feature set includes an API gateway, customizable portal for onboarding partners and developers, monetization, and deep analytics around APIs. You can use Apigee for any HTTP or HTTPS backends, no matter where they are running, on-premises or any public cloud. API Gateway enables you to provide secure access to your backend services through a well-defined REST API that is consistent across all of your services, regardless of the service implementation. The 3 solutions provide tools for services such as user authentication, monitoring, and securing, also for OpenAPI and gRPC.
Okay.
You will now design the APIs for the microservices identified for your application. The aim of this activity is to gain experience designing the APIs and considering aspects such as the API URL structure, the message request response formats, and versioning. Let's say we were defining an API for an online store. The API might look similar to what's shown here. Whether a service provides a user interface or some backend functionality, it requires a programmatic interface that is callable via HTTPS. The only difference between a website and a web service is the format of the data that is returned. For a UI service, we might return HTML, but a backend service might return JSON or XML. Use the principles we have discussed in this module so far and refer to activity 5 in the design workbook.
Okay, let's continue then. I'll put in pause the next video.
In this activity, you were asked to
Okay, and yeah, let's put a background here. Yeah, it will be this. Okay, let's skip. Let's just continue now. Okay, design REST APIs. So fill in the table on the next slide with your services and their resource and operation as shown in the example below. So in this case, we have some account service. I mean, they're referring to this account service, which will perform on transaction one of these methods: list, deposit, withdraw, transfer. Therefore, we'll select some of our services like write customer database, interview form service. So the interview form service will act on the collection customers. Yeah, because accounts database acts on transactions. Wow, this is kind of strange, unexpected, but maybe I don't have an understanding of that example. Here, for the interview form service, we can write a customer interview. So the collection will be interviews, right? Let's see, list, deposit, withdraw, transfer. It's just right for us. Then we have the itinerary definition service. Let's copy this and paste it here. Okay. So first of all, it will act on the collection of the interviews. It will read it. And then for the same service, we'll have the collection of itineraries. And we'll do a write. Okay, then we have the itinerary view and modification service, which will allow our trip director, but also our customer, to work on itineraries. And this service will allow to view updates. Let's see an example here: list, deposit, withdraw, transfer, modify. I mean, the modification will be executed by the administrator. Therefore, here we'll have also a method called propose modification, like comment, view, comment, modify. Okay. Let's just put some uniformity here. Oh shit. No. Okay. Nice. Therefore, we have some example of REST APIs. I'm not sure if this completely makes sense. It will need a review, but it's just the exercise for now. We accept it.
RESTful API for the microservices used in your case study. Here's an example for our online travel portal. Obviously, our API would be larger than this, but in a way, the APIs are all more of the same. Each service manages and makes available some collection of data. For any collection of data, there are a handful of typical operations we do with that data. This is similar to Google Cloud APIs. For example, in Google Cloud, we have a service called Compute Engine, which is used to create and manage virtual machines, networks, and the like. The Compute Engine API has collections like instances, instance groups, networks, subnetworks, and many more. For each collection, various methods are used to manage the data. For example, here are the methods for adding, managing, and deleting firewalls. When you design your APIs, you should strive to be as consistent as possible. This will make development easier and will also make it easier for clients to learn to use your APIs.
Okay. So a good design will need to keep in mind that will not be the only users. There are high probabilities that actually will not be the most frequent user of those APIs. They need to be explicit for the users that will try to make use of them. Therefore, we'll do the module quiz now. And the first question is, you're building a RESTful microservice, which will be a valid data format for returning data to the client. I mean, it says a valid data format, so I would say that we have two right answers. HTML. HTML might be correct. I'm not sure. Let's see. Because it sounds in my head that can be correct, but I'm not sure if it's something done normally.
Let's talk about the design of microservices.
So let's see. Okay, also HTML. Then which below will violate 12-factor app best practices? Store configuration information in your source repository for easy versioning. Treat logs as event streams and aggregate logs into a single source. Explicitly declare and isolate dependencies. Keep development, testing, and production as similar as possible. I'm not sure about this. I mean, I'm not sure where I have to store the configuration information. And I will not store it in my source repository. I'm not sure about this. And this statement about logs, which says treat logs as event streams and aggregate logs into a single source, looks logical to me. You've re-architected a monolithic web application, so state is not stored in memory on the web servers, but in a database instead. This has caused slow performance when retrieving user session though. What might be the best way to fix this? If I'm not wrong, we have to decouple front end and back end, and for stateful services, we're going to use Redis. Yeah. Here it's saying move session state back onto the web servers and use sticky session in the load balancer. This also may make sense, but I'm not sure why to say that this solution makes more sense. So let's see what might be the best way to fix this. We're trying to avoid slow performances, and the sticky sessions are not for making something faster. It's to making something actually working it. In some cases, we will need the service to be directed to the same backend which replied as in the first request. Therefore, if we decouple front end and back end, the front ends will use some information to send, they will be all directed to the same group of backends for that service. Therefore, this will not be needed anymore. Instead, the memory store in Redis will be needed, as the backend services will always be able to save some informations in Redis. Okay, yeah, this explanation makes sense for me. So make sure all web services are in the same zone as the database. This is not completely relevant. Increase the number of CPUs in database servers. Okay, that's not relevant in this context. So you're writing a service and you need to handle a client sending you invalid data into the request. What should you return from the service? A 400 error code. Let's see if I'm good at this. Okay, so 100% score, night. Nice one, nice one. Congratulations, you passed this assessment. So let's see the explanations. Okay, this is clear. Correct, code and config should be separated because config varies across deployments, but code does not. The true test is whether the repository could be open source without compromising any credentials. Oh, nice. Nice one. So let's remember that the code has to be exposable to the public without compromising anything. And then we have services should be stateless, and a service like memory store for Redis provides a fast caching service to store state. They enable services to be stateless and support scale and high availability. Okay, next.
In this module, we focused on microservice design and architecture. We started out defining what a microservice architecture is and the advantages and disadvantages of using microservices. We also enumerated some microservice best practices. Then we covered how to design service APIs and implement a REST-style architecture.
Let's mark as completed this. And
This module introduces DevOps automation.
So for this session, it's all. I will close the video here, and yeah, it was an intense one. Thank you for being here.